Okay, so we got our three categories here of electron pushing arrows. We can have bonds being formed, bonds being broken, or a bond being broken and formed all in one shot in our chemical reactions. All right. So let's take a look at at an actual reaction mechanism here. We did so for an acid base. All right, now we're going to do so for one of these addition of alkenes. So this would have been from your first semester. One of the first set of chemical reactions that you study that are unique to organic chemistry is focusing on alkenes. Alkenes are so much more reactive than alkanes because they have that pi bond pair of electrons. All right, so we're going to take a simple alkene here. All right, and this is an addition of HCl. Okay, let me just say we're going to study a bunch of reactions in this course, and a lot of people ask me, like, how do you keep all these reactions in your brain? For me, I have to keep them in these little categories. So knowing that this addition of HCl, keeping that word addition in mind, that is what's helping my brain keep track of all this information. I feel like sometimes when we talk about the names of these reactions, people are like, boop, not trying to remember that. That seems like extra information I don't want to fit in my brain. You kind of need it to help contextualize the rest of the stuff, right? Otherwise, you're just trying to memorize stuff. It doesn't really work that way. Your brain likes to put things in little boxes to the extent that we can like categorize our reactions. That's what's going to help you keep track of them. Okay. So, anyways, we call this one of the many reactions that we throw under this addition category when we were talking about alkenes. All right. Okay. So our product here, it's called an addition reaction because on one side of that double bond, we're going to add a hydrogen, and on the other side, we're going to add a chlorine. All right, but this reaction, we're going to have to do our mechanism here. We're not going to be able to do this all in just one shot. We're going to have to break it up into these two steps. There's going to be what we call an intermediate in this reaction here. Very common intermediate, we see it quite often, what's called a carbocation intermediate. All right, so our first step here is going to be one of those electron pushing arrows where this pair of electrons reaches out and grabs that hydrogen, and this pair of electrons jumps onto that chlorine atom. Okay. Cool. So first of all, let's see if we can throw these into categories here. We have those three categories: bonds being broken, bonds being formed, and then the double, bonds broken and formed. All right. So this one here, let's start with this one. What is happening in this electron pushing arrow? Am I making a new bond? Am I breaking a bond? Or am I doing both? I'm going to be breaking this bond between my hydrogen and my chlorine. And where is that pair of electrons going to go?
Chlorine.
Onto the chlorine, becoming specifically what type of electron? Bonding or lone pair? It'll be a lone pair, right? So when our bonds get broken, a bonding pair of electrons is converted into a lone pair of electrons. Okay? And then what about this one here? Now it starts at a pi bond and reaches all the way over to this other guy over here. So is this a bond being broken, formed, or both? This is both. All right, so everybody take a second and see if you can't draw me my intermediates in this reaction mechanism here. right, so now I have my new bond between my hydrogen and my carbon, and I also have this chloride ion. All right, I'm going to draw my chlorine with its extra pair of electrons. That means it has a negative charge. And I'm not done here. I'm missing something very important from that intermediate. Carbocation, right? So I think I said there was a carbocation intermediate. So maybe I gave away the punchline here, all right? But looking at this mechanism, how can I also tell that there's a positive charge missing? Not net neutral, right? Again, that conservation of charge business. Just a very easy double check when you're doing your mechanisms. Charges are kind of the hardest thing to keep track of, quite frankly, right? So having these little checks to make sure that we're doing things correctly. I'm starting out with two neutral compounds up top. I better have a net neutral charge for my intermediates as well, right? So in particular, where is that carbocation? Well, if we look, this new bond, let's say between the blue carbon and the red carbon, the blue carbon got to hang on to that pair of electrons, right? This pi bonding pair of electrons is now what is making up that new carbon-hydrogen bond. So it was that red carbon that got that pair of electrons snatched away from it, right? So this adjacent carbon here is where my carbocation lives, okay? So now there's one more arrow we need to finish it off. Everybody take a second. Given that we have our intermediates, we have where we're starting and where we're ending, draw in that missing electron pushing arrow. Should it be a bond breaking, bond formation, or both arrow? Okay, I need a bond forming, right? So I have no broken bonds anymore. I've already broken everything that needs to be broken. The only thing I need to do is to form this new bond right here, right? So what did we say for our bond formation arrows? We need to start at a lone pair, and we need to end at the atom that's accepting that pair of electrons. All right, so where am I going to start my arrow? At a lone pair. The only option here actually is that chloride. And I'm going to end at that carbon that's accepting that new pair of electrons. Okay, so now we have this bond. So this is a good illustration of all of our three different categories here. We have in the first step that both starting at a pi bond, reaching over and grabbing that hydrogen. We have a bond breaking arrow, and then we also have that bond formation arrow in our intermediate here. So, right, so we got our three different electron pushing arrows, reaction arrows here in this example. Okay. One thing to note about these addition reactions, since we're talking about carbocations, not all carbocations are created equally. Some are more stable than others, depending on how many other carbon atoms are bound to that carbocation carbon. So what do I mean by that? So the least, we're going to rank these from least to most. And we're going to kind of update this table as we move throughout this course. All right, but the least stable of all our carbocations would be when carbon is bound to no other carbons, what we would call a methyl carbocation. All right, if that carbon is bound to just one other carbon, we call it a primary carbon. If it's got two carbon neighbors, we call it a secondary carbon. And if it's got three other carbon neighbors, we call it a tertiary carbon. All right, so methyl, you'll literally never see a methyl carbocation. All right, they're the least stable, followed by primary, then secondary, then tertiary. All right, so in my previous example, I did a symmetric alkene. So it didn't matter which side of that double bond you chose to be your carbocation, you'd get the same answer, all right? But that's not always going to be the case. Okay, so let's do another addition of, we're gonna mix it up, HBr. I want everybody to take a minute and see if you can't draw me the reaction mechanism here for this chemical reaction. All right, complete with your electron pushing arrows, your intermediates, all that. All right, I'm going to kind of quietly start to fill in up here, so if you need any hints, you can look up. All right, in particular, I'm going to draw the structures for my intermediate and my product. All right, and you want to try to fill in the missing electron pushing arrows. We can always leave our hydrogens implied. In this case, it might make things a little bit more clear if I explicitly draw it in there. All right, so if we look at that first step, did we make any new bonds? Yes. Did we to be clear, this guy right here is one that we made. Did we break any old bonds? Yes. How many old bonds did we break? 2, right? So we broke both this pi bond here and this HBr bond, okay? So that first arrow that we're going to need, that pi bond is actually probably better to color in green here because that's where that pair of electrons ended up going. Right, so this pair of electrons, we have one of those breaking and formation arrows. Okay, but we also got to show that HBr bond being broken. So we're going to start at that pair of electrons, at that bond, and end on that bromine atom. All right, now, why do we talk about carbocation stability? Because specifically which one of those 2 carbons did I put my carbocation on? I put it on the one with the higher degree of substitution. I put it specifically on the tertiary carbon instead of the primary carbon on the other side because your carbocation is always going to form on the more substituted carbon. Okay. And then I got one more arrow to finish this off, my bond formation arrow. And that will be that pair of electrons, bond formation. So that lone pair of electrons being dragged over to create this new bond with that bromine. Okay. Because my carbon now has 4 bonds, I drew it as a little bit more of a plus sign. To be honest, if you wanted to just kind of leave it similar to how it was drawn on the left-hand side, and then awkwardly draw on a bromine, I don't really care. All right. Typically, when we have a bunch of bonds, we space them out in that little plus sign. This is fine. I get it, right? Now you can kind of more easily see where the carbons on your left and right were, how they match up. Okay. So one more thing that we got to be aware of, and we're going to go quick, I guess, with regard to these carbocations are the shifts. Hydride and methyl shift. And these will occur if a more substituted carbon is next door to a carbocation. All right, so what do I mean by that? Let's take an example here. We'll use our last strong hydrohalide acid here. Okay, our first step is going to be the exact same. We're going to have that lone pair reach out and grab that hydrogen, and then this other bond breaking and a lone pair forming on the iodide. All right, we're going to actually need 4 steps here, so I'm going to leave a little bit more room. Okay, looking at my organic structure here, where should my carbocation go? This bond was between this blue carbon and this red carbon. Where's the carbocation going to live? Blue. The blue carbon, the more substituted of the two. All right, but actually before this iodide attacks, we're going to have this hydride shift occur. Okay? And how do I know that a hydride shift is going to occur? Because there is an even more substituted carbon located right next door to that carbocation. Okay? So I'm going to have to draw in one of my hydrogens, my implied hydrogens. All right? Because I need this pair of electrons is going to jump ship over here to my carbocation. All right, so I'll draw it in explicitly so we can see where that hydrogen went. But importantly now, my carbocation is located on the more substituted carbon, right? That carbon right next door that was more substituted. Cool. All right, so final step here. I think you guys can finish this off based on what we discussed before. All right, I'll sort of go quickly. If you need to go, that's perfectly fine. But the last step here would be that iodide attacking and forming that new bond. All right, cool. Good luck with your homework. Next week we'll start in. We're actually going to discuss these lab techniques, IR and NMR, because you'll be using them in the second semester pretty quickly here. What's up?
I tried to take the quiz before class started. I was asking for an access code.
That's what was on the board.
No. Okay. Sorry, I was.
Yeah, so every day when you come in, it'll be on the board.
Okay.